Good morning and welcome. Before starting, let me remind you of the change of room tomorrow morning. It is not here tomorrow, it's an exception. The room is needed for some other purpose, and that was announced in the very beginning. And it will be in S8, so in the central building in S8. So tomorrow, only tomorrow, the lecture from 8 to 10 from in S8. So, you have been doing exercise 10, and you have gotten acquainted with the A matrix to discretize the Laplacian in 2 dimensions. And the result of that for our exercise 10 is a temperature field. So in the example that we have been considering, we had given temperatures in the room that was the example on the old side except for the bottom, which was insulated, so we had no heat flux through the bottom. And you saw by discretizing the heat equation for steady state, we get a linear system of equations. So it's actually pentadiagonal with 5 diagonals. Globally seen, it is a block tridiagonal linear system. And then we have been solving that with the backslash operator in MATLAB, which is the ML divide. And you saw with radar that this is a nice feature, very nice function, but it comes to some limit when we have large matrices. Then it takes a very long time, if ever it gets solved. So therefore it is really important that we have a good control on how we solve the linear systems that arise from discretization of PDEs. Here it is an elliptic PDE, but we also get linear systems when we solve problems for parabolic and hyperbolic problems by implicit methods. Then we have to solve a linear system in each time step. So this subject that we are now going to look at is important. So it's the solution of linear systems of equations. By the way, this is the solution for exercise 10, so you have something to compare with. So, let us consider the general problem. So we assume that we have done the discretization and that we have formulated our linear system, and we consider it in the form that's matrix A times the unknown x is equal to some given right-hand side. So, and we assume here that A is a given. We assume that we have real numbers, n by n matrix. So now we use the little n as the dimension also of the unknown and of B. So, and consequently, B is then in Rn is given, and the solution that we are supposed to determine, that is x, that is to be determined. So that is our task. And remember, the x, it can be very different kinds of quantities. In the example from exercise 10, it's the temperature. But you have also seen examples for the velocity with radar, and also for the a string function. So it can be anything. Now, which options do we have? We have two major options. The first option is that you know from linear algebra, direct solution using Gaussian elimination or some other direct method. So where we just take this and solve it, and we have an algorithm that will give us, after a finite number of operations, will give us the solution. That's it. However, as we saw with the ML divide in MATLAB, we might get very large memory demand, and also the time consumed might be very large with direct methods. So we have another option, that is number 2, iterative methods. So we'll look at both of them. But we first start with the direct methods, because if we can use them, if they are efficient, then and appropriate, it's the best we can get. And we will actually use one of them quite a lot. So then we look first at direct methods. And the first type of problems that we shall look at is a tri-diagonal linear system. If you remember when we discussed the different discretization methods in space, we considered essentially a problem where we have a second derivative is equal to some right-hand side. We could say that's the simplest elliptic equation in 1D. And what we get there, both with the finite difference, the finite volume, and the classical finite element method, that is a tri-diagonal linear system. And also, if we would go not in 2D as in the example of exercise 10, but in 1D, as we are about to do actually in exercise 11, then you'll see we get a tri-diagonal linear system. So what does this system look like? So I think I need a bit more space for that. So it looks the following, and I'm following here the notation in the textbook. So we have in the diagonal, we have elements that we call D, D1, and in the upper off diagonal, we have an A1. And in the second row, we have a B2, a D2, and an A2. So this pattern continues all the way down, and if we are at some row J, we would have then Bj, Dj, and Aj. And that continues all the way until we come close to the boundary. And then we will have, let's see, the B, the notation is Nj is the last, so we will have Bnj minus 1. The neighbor will be Dnj minus 1. And then we will have Anj minus 1. So that will be the next but last row. And in the very last one, we will have the Dnj and the Bnj. So that is then our matrix, and above and below the diagonals above A and B, we have just zeros. So we have only 3 diagonals, therefore the name tri-diagonal matrix. And that is the matrix that we shall call A. So this matrix here is our matrix A. And then we have the vector of unknowns, and in our equation, for our problems, when we start with a problem formulated for some unknown variable u, then we will have the unknowns at the grid point. So it will be unknown at grid point 1, say x1, that's u2 at x2, and so on. And then we will have here the unknown uj that will continue. We will have here nj minus 1 and u nj. So those are our unknowns that we want to determine. And on the right-hand side, we have then our given vector. And again, here the notation is different from what we started off here. The notation is from the book. There they used the C for the right-hand side. So then we would have this nj minus 1 and C nj. Let's see here. So that would be then our system, and here this would be our unknown vector u, and this would be our given right-hand side, which we call now C. So you see the notation is a little bit different. So we call our unknown u and our right-hand side C. And the diagonal has the entries D, above the diagonal A, below B. So, and if this matrix is diagonally dominant, then we can solve it by Gaussian elimination without pivoting. But instead of using Gaussian elimination, we shall use LU decomposition, which is just another way of doing it. So we can say if tridiagonal matrix A is diagonally dominant, so what does that mean? That means that the absolute value in the diagonal is larger than the sum of the off diagonals. So in our case it means then that the dj is larger equal the absolute value of the off diagonals, that is aj plus bj. So that should hold for all, and that should be for all j. In our case the j is from 1 to nj, and we should have that this holds with a larger for at least 1j. And in our case we have actually 2 of that, or usually we have 2 of that, and in fact it is when we come into the first row and in the last row. And so in our case we have then that the d1 is larger than the a1, and in fact we have also then that the dnj is larger than the bnj. So that is what the diagonal dominance means in our case. And if you remember from, well, it's a time ago, but in our discretization for, say, minus uxx equal f of x, so when we had this discussion in the beginning, say f of x, then when we do the discretization, you remember then we get a 2 divided by delta x squared in the diagonal, and we get a minus 1 over delta x squared in the off diagonals. So then this is satisfied with an equal sign, and this is clearly then satisfied with a larger sign. So this is okay for us. So if this is the case, then the linear system that we are considering here, A u equal to c, can be solved by, and we shall see that, LU decomposition followed by forward slash, but the important thing is without pivoting. then using forward-backward substitution, we add that and forward and backward substitution. And that algorithm that we are going to see in a minute is called Thomas algorithm. Another name for that is used mainly, or quite a lot actually, in the people doing incompressible flow simulations. It's called TDMA, called Thomas algorithm, or TDMA. That stands for tridiagonal matrix algorithm. So that is, so you will quite frequently see one of these names in the book. They use Thomas algorithm. So, regarding the LU decomposition of the matrix A, LU decomposition we make the following ansatz. That is, that we say we assume that we can write our matrix A as a lower triangular matrix times an upper triangular matrix. That is, we assume the following form. We have in the lower triangular matrix, we have only ones in the diagonal. Let's see. So this is a diagonal, should be a diagonal matrix, where we have only ones in the diagonal. And in the lower diagonal, subdiagonal, we have, so we have also here then a 1, we have a beta 2, and so on, beta 3, and so on. To the last one is called beta nj. So the B that we had originally in the matrix will then be changed into something that we call beta. We have then 0 still below, and all the upper half of the matrix, so above the main diagonal, is all 0. And that is a lower triangular matrix. That is multiplied by an upper triangular matrix, where we have some entries. I call them delta 1, delta 2, and so on. And the last one is delta nj. So those are in the diagonal. And above the diagonal, we'll have a matrix, not a matrix, we have a diagonal that is identical to the one that we have in the original matrix A. So it will have then A1, A2, and so on. And the next but last will be the A, N, J minus 1. So A, N, J minus 1. So it's similar to what we have in the A matrix. And above this subdiagonal, above the main diagonal, so containing the A's, we have just zeros. And below the main diagonal, we have also just zeros. So that is then a lower triangular matrix. And that is the lower triangular matrix L. And this is then the upper triangular matrix U. So that gives the name lower times upper. So it is simply an ansatz that we do. And if you would do Gaussian elimination, and you would not need to do pivoting, pivoting is to interchange the rows, then you would get this U, that would be the form that you get in the end. And the L, you don't need to do anything with the diagonals, but these coefficients will be then the coefficients that you have to multiply the rows in containing the pivot with to eliminate the values below the pivot. So that is from Gaussian elimination. So you get it in fact also from there. But we want to now get it from this ansatz. What we simply want to do is we want to do this matrix multiplication and equate it with A. And then we shall see that we can find out what the betas, the deltas, and the should be. The A's are unchanged. So we just do now this matrix multiplication LU. So, what we get is, to do this multiplication, we need a little space here. So we simply do now 1 times delta 1, so that is all what we get from there. 1 times A1, so we just get the delta 1 and the A1, that is easy. A1. Next one, next row, beta 2 times delta 1 will be the first, and then we will get, let's see, we will get first we will get the beta 2 times delta 1, and the 1 times 0, nothing. So the beta 2 times A1 plus 1 times delta 2. So we just do it now, matrix, we do this operation of the second row with this matrix. So we get then the beta 2 times delta 1, no more, because below the delta 1 of U we have just zeros. And here we will get the beta 2 times the A1 plus, let's see, delta 2. So that will be that component. And then, let's see, we will also get a contribution in the third from this here, when we do the beta 2 times 0 plus 1 times A2. So then 0 doesn't give any contribution, so we'll get an A2 above the diagonal. So this is in the diagonal. And the next one will be then, we have here then the 0, the beta 3, the 1, and then we do this multiplication, and we will see we'll get a 0 first, then we'll get a beta 3 times delta 2, so that is, this is in the diagonal. So this is 3, 2. Now we get again in the diagonal, and I write it in this form to make it clear. Beta 3, A2 plus delta 3. That is sitting in the diagonal. And the off diagonal will give us just A3. So this pattern will continue all the way through. So that means we have then in the diagonal we have these larger expressions, and we get to the very end, we'll get something in the diagonal where we have the beta nj times the a nj minus 1 plus the delta nj. So that is, we follow this pattern. You see, is always the beta times the index of the row times a of the index 1 less plus delta with the same index as if the row we are. So that is that. And then above we will simply have the a nj minus 1. So this pattern continues, and in the left neighbor of the diagonal element, that will be then following this pattern here. Then we will get here the beta nj times the delta nj minus 1. So again, you see also that pattern. And above and below, we have just zeros. So that means we have, of course, as we should, a tridiagonal matrix, this LU product. And now, when we have this, we can equate what we have here, the LU, with the original matrix that we started on. So, of course, what is given is the matrix A, with diagonal D, upper diagonal A, lower diagonal B. What we want to determine is the betas and the deltas in the L, the lower triangular matrix, the beta, and the upper triangular matrix, U, the delta. And this equating gives us then the chance to do that. So then let us do that. So we are now creating the components of A and the product LU to find out what the deltas, the betas and deltas are. So we start with the delta 1. The delta 1 is equal to the D1. So that is easy. The beta 2 delta 1 is equal to the B2. So that means the beta 2 is then equal to the B2 divided by the delta 1, which we already know. So we can use that already. Then we go into the diagonal element here 2, 2. We equate that with the D2. Remember, we know already the beta 2, and we know, of course, the A1. By that we can determine the delta 2. So the delta 2 will then be the D2 minus the beta 2 A1. So that's no problem because D and A are given and beta 2 we all know already. Beta 3 is equal to, so that is this one, that will then have its counterpart here as the B3. So and so on. So we can just write this one, B3 divided by delta 2, and then this diagonal element will be equated with the D3. So we know already the beta 3, we want to determine the delta 3. Delta 3 is then equal to the D3 minus the beta 3 A2. So we see here the pattern. So from that we can then see what the algorithm will be to determine the deltas and the betas. That is then gives us the LU decomposition. So from that we see LU decomposition. Before we did the ansatz, L times U, but now we get the elements. For the D, the delta 1 is equal to the D1. We have to start at some point, but then the pattern you see repeats itself here. So we can say then the beta j is equal to the bj divided by the delta j minus 1. And the delta j in turn is equal to the dj minus beta j times aj minus 1. So, and what we have here, this here, that is then done for j from 2. 1 we don't need to do. We have the only delta 1 we need there. And we do that until nj. So that is then to get the components of the lower triangular matrix L and the upper triangular matrix U. Just this. So it's a so-called recursive formula, because we can only do the computation of delta j when we have done beta j. We can only do the next one when we know j minus 1. So that makes it then not suitable for a vector computer. Vector computer, you want to do the same operation for all. You cannot do that with a recursive formula. But okay, we have to live with that. So then we have the LU decomposition. And now we imagine, when we look at this, we see once we have used the bj, it is no longer needed. You see what is needed here is the beta j. So that means what we can do is we can overwrite the bj with the beta j, so that we simply, because once we have computed this, we don't need to store it. So we just overwrite the bj with the beta j, and also with the dj, you see here, once we have computed this delta j, dj is no longer needed. So we can overwrite the dj with the delta j. So that is then actually done. We use the assignment. It is when you write k is equal k plus 1, you always use you overwrite then the k with the new one. We can do something similar here. Could use new variables, but it's not necessary. So that is, it's usually done that you just overwrite. So if the dj is overwritten by the delta j and bj by beta j, we get the algorithm as it is usually implemented for the LU decomposition. So that is then the first part in the Thomas algorithm. And then, if we do that, we don't have to do the D1 then already contains the delta 1. We have not to do anything there. We just do start here, and we do it in the following way, that we say the bj is then equal to, and I use now this way, and I use that as a computer assignment. So So this notation, as I use it, as you write in MATLAB or any other programming language, for example, k is equal to k plus 1, then you overwrite the k by the new, and that is the same thing. So I use that as computer assignment. So then that is equal to dj divided by dj minus 1. So then we just use then on the place where we have stored dj, that is then overwritten by what is our beta j. The same for the dj, that is then taking the role of the delta j, which is dj minus, and now we can use the bj here, which is the beta, times aj minus 1. So that we do from 2 to nj. So then this is the thing that you need to program. Of course, when you do the programming, you just write dj equal to and so on. The only thing that you have to be a little careful with is that the bj has a component b1, which is not needed, but since we are using the notation starting with beta 2, you have to assign it the same vector length as you have to assign to the diagonal, the d. That's a little, but that's just a technical thing, but you'll see it quickly when you do the programming. So then we have the LU decomposition, and then what we want to solve is AU equal to C. Now we have an equivalent thing, because we have now that A is equal to LU. So now we solve this. And how can we do that? How can we solve that? Well, the trick is that we solve it in 2 steps. First we solve L times, let's call it Y, equal to C. So then that is that, and so then this is solved by 2 steps. That is Ly is equal to C, and that is then the lower triangular matrix sum unknown that we determine is equal to the given right hand side. When we have determined the y, we solve this problem. The upper triangular matrix U times our unknown that we are really interested in equal to the right hand side. So then that will be U times little u is equal to y. So then in these 2 steps. So that means we have then to solve the problem first Ly equal to C. So the Ly equal to C, that is the first problem. And then we have the matrix L, that was the 1, had the B2, the 1. You see, I use now the notation with the overwritten ones. It should be the beta 2, and so on, but I use already the overwritten notation here. B3, 1, and so on. Then we end up in the right corner. Here we have the B and J. So that is Bj is equal to the beta J here. So remember that. That is our L matrix. And our unknown is then called Y. Y1, Y2, and Y3, and so on, y, n, j. So it's an nj vector that we have to determine, and C, that is our given right-hand side that we had from the very beginning. So that is then our problem to solve. That is our L matrix, and that is our Y, and that is our right-hand side. Then you see how we proceed. We start in the first row. So from that we get that the y1 is immediately, can we immediately see that is equal to the c1. 1, of course we have just zeros here and zeros here still. Then we want to determine the y2, and the y2 is then equal to the c2 minus the b2 times the y1, right? So we do this times this, and the y1 is already determined, the c and the b's, and then the y3, if we take that as another example, that would be equal to the c3, and then we would have here the b3 times the y2. B3 times the y2, and so on. So that would be then the pattern that we get to solve for y. And what we then get is the forward substitution. So that is what we do here, forward substitution. That is the Ly equals C. That is in the following algorithm. We have then the y1 is equal to the c1, and the yj is equal to the cj minus bj times yj minus 1. That is j from 2 to nj. And again here we can do the same trick as before. We can overwrite things. So then if the C is overwritten, by y, we get, or we could say the cj, we do it step by step, we get the algorithm for the forward substitution. Following. So again, the reasoning is similar as we had before. We observe once we have computed the, for example, for yj, then we have used the cj, then we don't need that any longer. So then we can overwrite the cj with the yj. So then we say that the cj is then, again I use the same notation, is overwritten by, so again this is a computer assignment, by cj minus bj cj minus 1. You know, once we use that, we also have then to use this is then has been overwritten as the C. When we start, it is already right, and so it was then this. That is then from 2, j from 2 to nj. So that is the next thing that we have to program. And we can already look forward. What remains to be done is then to solve the problem u equal to y. So that is then to be solved. So that is then, and in our case that becomes that problem because we have overwritten the y by the c. So c is overwritten by y. Let's see. Yeah. So then that becomes u equal to c. So then we have to solve this. And that will be then done by backward substitution. So that is what we call LU decomposition. The thing that we had in the beginning, to get the L and the U, that is LU decomposition. What we have here is the forward substitution to get the intermediate solution y. And what we are going to see after the break is to do the backward substitution to get the final solution. And all that together is then the Thomas hybrid. It's the same procedure that you do also with standard LU decomposition without pivoting. That is always the prerequisite. We don't do row change, that is called pivoting. We don't need to do that if the matrix is diagonally dominant. Okay, so we stop here for 15 minutes. 15 minutes, right, we have Thursday break.